All right, everyone. Thanks for attending my talk, Maximizing Builds, the NativeLink overview. So large-scale projects, particularly those using monorepos, face unique challenges as they grow in size and complexity. And addressing these challenges requires tools that can enhance, one, the build process, two, you optimize the testing, and then three, streamlining deployment, and particularly deployment at scale. And this is where NativeLink steps in because it's designed to maximize build and test efficiencies for large code bases. So I'm Nadine. I'm a NativeLink contributor. I work closely with Aaron on the NativeLink project. And my past experiences have heavily focused on databases ecosystem, anywhere from analytical systems to data warehouses and lakehouses. And I previously worked at DevRel at OneHouse, Rockset, and Bose. So let's talk about the challenges with monorepos. So you can think of a monorepo as like a big bookshelf. And inside this like shelf, there are a lot of books. Books could be synonymous to projects. And basically a monorepo hosts a whole bunch of projects in a single large repository. And monorepos are good for a couple of reasons. If a project shares the same repository, changes to a common library can be instantly available to all projects that depend on it without the need for versioning. The second thing is that every project in a monorepo are kept in the same version. So there's no version drift. This keeps projects all consistent because let's say if you have two projects in separate repositories and one gets an updated version, there's a highly likely chance, depending on how your teams are managed, that the next project might get it a couple of days later or maybe not at all. So that's a big point. It's also easier to make changes to the project in mono repos if you need to refactor code. So let's say if you refactor code and multiple projects are affected, you'll have to update all those projects all at once or else your builds will fail. And the other major point is that if all dependencies are in one place, more than on average, monorepos will probably encounter less integration challenges. So if you're thinking about adopting a monorepo, there's some considerations you might want to, take in. One is you'll need specific tooling. The second thing is you'll probably need to work with like your build engineers or your DevOps folks to see how it can, you can embed it in your current infrastructure, for example, your CI/CD workflow, your build tools, and so on. And then you'll also need a migration strategy if you have multiple projects and you want to combine them into a single repo. That will also need to be taken into consideration. But it's not all fun and glory. There are challenges when it comes to large projects with monorepos. A good example of a monorepo is like the Chrome project. So one of the challenges is scalability. If you have a lot of developers contributing to a repo, you also have to increase your compute. If you don't, you'll definitely hit bottlenecks. For example, one of the things you'll have to do is you have to build more frequently, and you might need to increase the number of parallel processes you're running. And this can come at a financial cost. The other challenge is you might encounter long build times if you have to wait for hours for build to be completed. And as a result, you'll probably wait more. So you might move like at a slower pace. And this can be exacerbated by like integration conflicts and things like that. The other thing that you might encounter is you may want to implement selective builds and tests by running only the processes that are necessary based on the changes that you've made. And again, this part requires some sophisticated tooling so you can track your dependencies and integrate them with the build system. And finally, one other thing to note is that handling dependencies effectively is needed for stability and reliability. Multiple teams working in the same repo can lead to conflicts between different versions of the same dependencies, which can be difficult to resolve without affecting, certain parts of the project. So you need to ensure that the builds are reproducible across different development environments when dependencies are involved. And this can be challenging. And to note, this part that I just talked about is called hermeticity. So before we talk a little bit more about hermeticity, how many of you have heard of Bazel or are familiar with Bazel? I'm just trying to get like a temperature gaze. So we have 1, 2, anyone?
3 people here.
Oh, cool. Okay, so this might be familiar territory. So Bazel is open source for those of you who it might be new. Bazel is open source and is designed to support automation of building and testing software. And it helps overcome the challenges that we just talked about with monorepos. Bazel can build applications for different platforms like Linux and Macs, and also across different architectures as well. And Bazel is great in handling large complex processes, but in terms of hermetic builds, it creates build outputs that are deterministic and reproducible. And this is achieved by isolating the build environment from the host machine. So Bazel does this by using what they call a sandbox to ensure that the builds are isolated from each other and from the environment. And if you guys have any questions throughout the point of the presentation, feel free to pop them in the chat as well. And then one of us will be able to answer it. I can answer it at the end. So we talked a little bit about hermeticity. This is a definition of it. It's just being airtight or gas tight. Basically, when you're running your builds, you don't want to have any like outside conflicts besides the dependencies that the builds depend on. So what does Bazel not do out of the box? So while Bazel supports remote execution, like it has the remote execution protocol, it does not provide a built-in server for it. You must actually set up your own remote execution environments. But also setting up the remote caching on Bazel is a very manual process, and you have to do the setup and maintenance, and the maintenance can be sometimes difficult to maintain. Bazel does have local caching, and it does support remote caching, but again, configuring managing remote caches can be complex. Now, in terms of hermeticity, Bazel aims to provide a sandbox environment to isolate builds, but achieving true hermeticity, like airtight hermeticity, in Bazel is challenging due to the dependencies on the host machine and its environment. So truly achieving hermeticity, like sealed environments on Bazel, is hard. So let's say you have GCC5 installed on your system. Bazel will use this version when compiling code. Another system might have GCC 5.1, and then Bazel will use that version as well. And this drift or variance can lead to inconsistent builds across different machines. Bazel looks for tools and dependencies in the standard system path. So if the required tools are found in these paths, they're used for the build. And this is the challenge because it will cause cache misses between machines. So Bazel's rules, to note, Bazel rules can be configured to download specific binaries and place them in controlled locations, but these rules need to be meticulously defined to avoid any unintentional dependencies on the environment. So this leads us to NativeLink. So NativeLink is open source and is designed to enhance the build process of large complex projects. And NativeLink offers a remote out-of-the-box remote execution server that integrates with Bazel and other clients like Buck2, allowing you to build and test actions to be offloaded to more powerful remote machines, or in Bazel in this case. So this allows you to optimize resource usage and reduce build times. NativeLink also has a global CAS. So CAS stands for Content Addressable Storage, where build artifacts are stored. And these artifacts can be reused across different builds and machines, meaning you don't need to rerun parts of your build if nothing has changed. So let's talk a little bit about caching and remote execution. So caching is just a component of remote execution where build artifacts are stored. By caching the artifacts, you can avoid doing rebuilds. You can just pull down the artifact that you need. Now, remote execution basically refers to the process of running basically computational tasks, such as building on remote servers rather than doing it on your local machine. So by using remote servers, tasks can be distributed across multiple servers. So this is what we call parallel processing. And this is how you can speed up build and test processes so much faster. So more than average, like unless you're like the 1% of people who have these like super mega computers, on average, the remote servers are more powerful than local machines. So they can handle more tasks, allowing you to build, to have the builds be a lot faster too. And there's also a scalability component because you can horizontally scale by adding more compute as your team grows, as your development team grows, basically. So this is the NativeLink architecture. And it's basically designed to optimize build times and processes for like monorepos or basically any large complex process by using remote execution and caching. And there's a couple of components that you see here. You have You have the client, which interacts with the build system. In this case, I'll be walking through through the example with Bazel, but it could be Buck2 and Reclient or whatever client. Then you have the scheduler and worker pool. These manage and execute the build jobs remotely. And then you have the CAS at the far end. This is the content addressable storage, and this basically is like your blob storage or a day lake or something like that that just stores your build artifacts for reuse. It's just a storage thing. So with the client, in this case with Bazel that I'll walk through an example, let's say Bazel will initiate a build, or a client will initiate a build request and interact with the remote execution and caching services. And Bazel is commonly used because it's widely adopted. Now we have the scheduler. This is like the schedule pool that you see on the diagram. It manages and assigns the build tasks to the worker pool. Now, the schedule ensures that the tasks are distributed efficiently across the workers. In this case, it's the worker pool, basically to optimize for performance and be mindful on resource utilization. And then you have the worker pool. The worker pool is like not the smartest. I think the schedule is the more smarter one. The worker pool just basically, gets the task and builds the code. Workers compile and link the code, creating the build artifact. So the worker pool can consist of multiple workers running on the remote machines, basically. And the remote machines basically provide compute resources compared to, the local environment, which we chatted about earlier. And then you have the CAS. This is just the storage. It just stores the build artifacts, and it just ensures that once a build artifact is created, it can be reused for future builds. And the importance of this is that it avoids redundant compilation and linking. So the storage system is essential for caching, and the caching is actually one of the ways that you can reduce build time and also save on huge resource usage. And I'll talk about this flow and how this happens and why that is. So if we talk about the client interaction, you'll trigger a build by using Bazel. Bazel is the client, and it'll compile a list of tasks and dependencies required for the build. Now, before executing the build task, Bazel will check the CAS to see if the necessary artifacts exist. If it does, and the artifacts are found, it just retrieves them from the CAS. And then basically Bazel skips all the corresponding steps. So it doesn't talk to scheduler, you don't have any workers doing anything. And this is one of the ways that you can save on compute because of the caching. But let's say, Bazel makes a request the CAS, and the CAS doesn't have the build artifacts. So what will happen is that Bazel will send the request to the scheduler. The schedule breaks down the build request into smaller tasks that can be executed independently. Now, these tasks are then assigned to the worker and the worker pool based on the availability and resource. Now, the workers in the pool, in this case, the worker pool, execute the assigned task, and that's basically their main job. This involves compiling the source code into machine code, and then it links the compiled objects to create an executable, generating other necessary build artifacts. And the workers perform these tasks on the remote machines, and this is how you can leverage, compute resources and do parallel processing. Now, once the build artifacts are generated, they are uploaded to the CAS. So the CAS uses the content addressing to store the artifacts efficiently, and then it gets stored. So then for subsequent builds, the client, as I mentioned earlier, the client will first check the CAS to see if the required artifacts exist. If it does, it skips the redundant build steps and directly retrieves the artifacts from the CAS. So when we talk about before we talk about hermeticity, we need to talk about what a tool chain is. So I know there's a lot of definitions about tool chains, but the basic thing is it's just basically a set of tools and dependencies required to build and run a project. Now, what may be required can be like compilers, interpreters, libraries, and so on. So if your project involves C++, for people who have like a riff with C++, I'm just kidding, or Python, your tool chain might need to use Clang and Python 3. Now, within the Nix package manager, the packages are built in sandboxes. So the Nix builds, before I get into Nix, do people know about Nix here, or is this a new concept? Okay, Chester.
We've got maybe one person here who's familiar.
Okay, cool. Awesome. So within the Nix package manager, packages are built in sandboxes. The Nix builds are executed in package builds also called derivations. And if any input in the package changes, small or big, the dependency source code changes on what you're building. And so you'll need to actually rerun the whole build again. Now, this is different from Bazel. With Bazel builds, they're a little bit more fine-grained, and each action is a build and has its own sandbox. So if any input to the action changes, you would need to rebuild or rerun just that action. But the actions are finer grade than the Nix derivation. So you can get better incrementally and faster builds, but it does come at a cost with Bazel. So this is the trade-off. With Bazel, the trade-off is the incremental approach. You need to specify the build graph in a fine-grained manner. So unlike Nix, where you can specify the entire package containing, thousands of files at once, Bazel requires you to map all the files within each package. Let's say you have 2 packages, and each package has 1,000 files. You need to specify the 2,000 files. So ultimately, when you're thinking, if you don't do this in Bazel, like if you don't specify all the files for the build graph, you can get similar performance as Nix. So ultimately, it comes down to how much time you're willing to invest in optimizing your builds. So this is a Rust meetup, so it'll be good to talk about NativeLink. So I didn't say this earlier, but NativeLink uses the source code is Rust, and we're using Rust for a couple of really good reasons. One, Rust doesn't use a garbage collector, and this is an advantage because with garbage collection you can introduce latency. There's also the memory safety that Rust has. So Rust ownership system enforces strict memory management rules at compile time, so you can prevent common bugs, null pointers, data races, and so on. And Rust is also incredibly performant. And one of the ways it does this is because it does not have a garbage collector. So NativeLink can maximize on this and really have more efficient CPU usage and be able to handle high volumes of build tasks without a lot of overhead. The other thing is that there's Tokyo is a project, and it provides abstraction for async calls. And this allows NativeLink to efficiently handle numerous concurrent tasks as well. So I know like a lot of open source projects are primarily built in Java or C++. So basically the reason why, with Java and Go, for example, they're garbage collected languages, so there's some latency introduced there. And then C++ lacks the memory safety guarantees that Rust provides, and it can be really complex to manage memory and ensure thread safety. And obviously with Python and JS and other similar languages, they're dynamically typed and interpreted, so they're basically lower performance than Rust. So to recap, really, NativeLink is like designed to work with the clients like Bazel, Buck2, and Reclient that have the remote execution protocol. The difference is that NativeLink provides the remote execution server out of the box as well. And basically also NativeLink has a remote caching system, which we talked through in the architecture, that you can cache your builds. And if the build artifacts exist, then you can just pull them down and you can avoid doing redundant compilation and obviously save on compute resources. So it's really good if you're working with large complex projects and you need that type of efficiency. So on the roadmap, we are working on improving stability. We're also increasing our storage options, for example, S3 or Redis and things like that. And we're also working on fault-tolerant schedulers. So you can get involved with the NativeLink community if you want to learn how we're using Rust or interested in learning more about remote execution. There's a QR code if you want to scan. And then also, if you want to join the Slack, I'll make these available too, or I can share the link in the chat in just a minute. But if you click on the GitHub, this is a NativeLink, and you can start us on GitHub if you're interested in learning more. You wanna help us out there. And I think that's it for my presentation.
Okay, thank you very much for the presentation. I guess, yeah. So I guess, yeah, now would be the time to ask questions. So if anyone has questions, feel free to jump in. I think we've got a bunch of questions in the chat already, actually.
Yeah, so I had asked a question to follow up would you recommend if you're using Bazel, you should use NativeLink, or is there some level of complexity and size to justify it, or is it just something you think you could just jump straight to NativeLink versus out of the box Bazel self-managed, self-configured? That question.
So with Bazel, you can, it's complementary to NativeLink. Do you have like a more specific question around that, or?
Well, complementary, and so you can use Bazel without NativeLink for that.
You need a client.
Right.
So NativeLink, think of it as the server aspect, and then Bazel as the client. So basically, Bazel does like local caching, and it has the remote execution protocol, but it does not provide the server. You would either need to implement the server yourself, or you can use something like NativeLink. But the advantage is the parallel processing, right? That's the advantage, and also the remote caching as well.
Can you talk more about the CAS?
Yeah.
So that's integrated into NativeLink, or is that a feature of NativeLink, or is that something? This is an abstraction that somebody has to set up?
No, it's part of NativeLink. So the remote CAS is a NativeLink component. It's part of the architecture itself. It's not like something you have to find and then embed it in. It's part of the NativeLink project, basically.
So this is sort of, I guess they call the concept of winking. So you just bring in objects that have already been compiled. So this is only for compiled code. Is that correct?
Mm-hmm.
So for Python, or I guess one of those non-compiled, like bit compiled languages, it doesn't really make sense to have that, or it's a wasted resource, or is it an option to install it, not install it? I don't know. Any other details, or is there a doc I can go read? Is it on your GitHub?
Yeah, there's a GitHub, and I can try to find a doc. We are working on like building more content around this, but I'll let Aaron jump in. If Aaron, are you still there?
Yeah. So I would argue that for raw Python, like pure Python, it probably doesn't make too much sense, like because you don't compile it. For tests, on the other hand, it can make sense if you have long-running Python tests and you can distribute them. And when like something that is fairly common, I would say, is when you have, for instance, C++ linking to Python, or like Python loading some C++ libraries, then you might want to to build those C++ libraries in a distributed fashion, and then also just have the Python interpreter running. So that's I think so. It can make sense, but it kind of depends on the size of the project, I would say.
So then what's the interaction between something using like Bazel and NativeLink's CAS?
If you would run Bazel without NativeLink, you would only get local caching. So you would have, so if you run a build on your machine, you would get caching and you would get incremental builds locally. But if you do this in a monorepo, you can't build the monorepo on your local machine. So that's kind of that's why you would want some kind of server component.
Yeah, so it goes back to earlier in the presentation where I talk about parallel processing with large complex projects. You can't really do that locally.
Yeah, so I guess this is transparent to Bazel. The user doesn't have to worry about setting up CAS or any sort of configurations for Bazel. You just basically use Bazel build, and then it does its thing. It automatically uses, okay. And then so for monorepo, it makes sense. But if you kind of have lots of different repos on Git, how does that work? It doesn't. I heard Aaron. I see Aaron smile, and so I guess that's the answer.
So, this is a very tricky thing. So I mean, you can take in Bazel, you can specify external dependencies as HTTP archives. You can also do the same thing with Nix, and in this case, it kind of boils down to do you want to have this fine-grained level of caching and fine-grained level of control over every external dependency. For instance, when you have, let's say, your C++ compiler itself or the Rust compiler, would you be willing to map out the entire source code for the Rust compiler with Bazel? Maybe not. So in this case, maybe it makes sense to not have Bazel manage this, but instead to just make some pre-built version available to Bazel. But then you run into the problem where Bazel gives you this reproducibility, but if you fetch it via some other mechanism, you lose this. And that's why one, in my opinion, very good solution is to use Nix to get those pre-built artifacts into the Bazel build draft so that you get this hermetic shell around your Bazel build.
Okay. That's what I was looking for. Yeah, thanks.
Yes, and then this is what we kind of
yeah. So the goal should be being as hermetic as possible. I mean,
Yes.
this is what the whole purpose of this is. Okay.
Yeah.
You mentioned Nix. Do you provide also like an environment for building Nix packaging and then the caching layer?
No. So we do integrate. We have glue code to glue native Nix toolchains into Bazel builds, so that you can use like a Nix environment and run Bazel builds inside that. But at the moment, we're not implementing Nix caching like the global Nix cache or something. But it's something that people have asked, and it seems like this is a very sought after thing to have. So maybe, like technically, from the NativeLink architecture side, it would be possible.
All right, makes sense. Thanks.
May I ask, without knowing any more about the Nix, other than I've chosen not to learn it. Life is too short. Could you elaborate on the Nix and maybe the scope? Would you say this prefers Nix OS or any Linux with Nix packaging in it? And anything else? Or is there any chance of Nix for Mac OS users, or would it make sense? What would make and what wouldn't?
So the question was if there was Nix OS or if you can use.
If this is if it is easier to use this on the Nix OS or just any Linux distribution with Nix package. As I understand, you can have Nix packages on any Linux distribution, right? And if there are any Linux distributions that are easier to use.
Oh,
with NativeLink.
I mean, I use Nix OS. Aaron?
I would say, so the thing with Nix is if it doesn't work anywhere. And if it does work, it does reliably work. But the thing is, like, if it doesn't work, then you really have a very broken build. That's the kind of trade-off that you make for getting this perfect, like you get reproducible errors. It does work on macOS, so you can use it on macOS. NativeLink itself does not support multi-cloud deployment for Mac yet, although this is definitely planned. You can run NativeLink locally on Mac. This does work. And like, if you're asking for recommendations in terms of like what kind of OS, I think it kind of doesn't really matter, because the Nix package manager, if you install it, it's air-gapped anyways. So one small asterisk is sometimes Rust C links in glibc, and if you use an older version, then maybe in some rare cases where, because of bugs, the glibc version leaks into the build, you could get mismatches. Yeah, if you have, like, I don't know, if you build something with glibc 2.30, and no, actually with a Nix toolchain that exposes 2.39, and then you try to run it on an older system that uses 2.30, it will not work. That's the only asterisk. So I guess any kind of system really, yeah, I mean, you could also work around this glibc issue by just using muzzle. So yeah, anything goes kind of, except for Windows, unfortunately. Yeah.
Well, I'm guessing Windows support is not great.
Thank you.
Cool. Thanks, everyone.
All right, thank you very much for the talk. So yeah, that's it for the talk. If there's any other questions or comments, I guess now would be the time, but otherwise, yeah, I'd say like if you want, you're free to leave now if you wish, or you can stick around and or you can just stick around and we can chat about other things. The meetup is scheduled to go for an hour and a half, so.
I think
I guess I have a bit of a question. Can you hear me from here? About the NativeLink? Unless if that's already. Oh, you can hear me? Okay.
Yep.
yes,
How, and this may be a little bit of a naive question because I haven't used those tools before, but how does it link in with your company's artifact repositories? And what I mean is like Maven or NuGet or pip, those internal repositories. Is that CAS that deals with that? Or is it sort of outside of that? And a mono repo is just building one big shared object, yeah, or something like that.
You can do several things. You could import, so you can import, for instance, Python packages like pip. Bazel has pip wrappers. You could also create, for instance, Nix derivations that contain these pip packages. And if you store, like, basically because you have like the full freedom to import anything from any external source, you can, yeah, basically use whatever.
I guess my question is, when I've built my artifact and I want to vend it to the rest of my company from my repo, what do I do in that case, right? Because my company obviously has a NuGet repository where we vend the results of our work. The pip teams, Python teams will have their own pip repositories. We have their internal repos from that. I guess how do the results? I know that they're held in CAS. How do they make their way out then to vend, against the larger teams?
You can just you can use CI for this. So the CAS objects, you can copy the CAS objects out of the build and into your repositories or registries or external storage things.
Oh, okay. Fantastic.
In the NativeLink architecture, you can just pull it down from the CAS directly. Yeah.
I see. Okay, that makes sense. Thank you.
Hey, so I want to make sure that we're all speaking the same language because I've been listening. I just want to make sure everybody understands the separation here. So Bazel, from the point of view, is the client. What we're providing is the execution service, which deals with actually, like, think of it like I'm going to run GCC, some point GCC or Rust C or insert Python, whatever you're running. At some point, that's going to get invoked on your machine. We intercept that through the protocol that Bazel provides and essentially distribute it amongst n number of machines, and it could be 1,000, it could be 1,000,000. It scales infinitely. That's the beautiful part of this protocol. The way it does that is it hashes the things that are visible. That's the detail I think that people are missing here, that where the part's getting through. So think of it this way. Bazel says user is installing or is compiling this GCC or Rust file, right? So there's a file somewhere, and then there's a couple other files that says, oh, here's the headers that accompany it. Oh, here's the dependencies that it's also grabbing. It bundles all those together, puts them into a Merkle tree, hashes that, takes that hash, uploads all the artifacts, then it passes that hash around. It finally gets to the worker, materializes from the hash, puts them back onto disk. Only those files are visible to that job, nothing else. So only the things that that specific job, that GCC command said that is supposed to be visible, is only visible to it. Then it executes the job, materializes the files that it's saying, the object files or binaries or whatever it's supposed to be, uploads them to the CAS. Okay, so again, we're not talking to the client yet. Uploads them to the CAS, does the same thing inverted, calculates a new Merkle tree of the output files, or file if there's only one, uploads that, takes that digest, it's just a hash, passes it back along the other way. So now you're dealing with like 40 bytes of information are just being passed from place to place, gets back to the client says, okay, I got the results, now go back to the CAS, download that, and materialize it back on disk. From the user's perspective, it didn't change. Everything was actually like as if you ran it locally, but it all happened behind the scenes. And that's what gives you that high parallelization. You're trading parallelization for latency. And keep in mind, the latency is quite low because all of those messages is such small data that it's super small. So you're talking like, you know, maybe microseconds, million milliseconds in reality. So does that kind of make more sense? So in other words, the question originally was, how do you get the files out? Well, Bazel put the files at some point somewhere, or your client, whatever your build system already did that. It still does that. We just did all the work behind the scenes, so it doesn't actually execute here. It executes somewhere else.
I get it. And my follow-up question was going to be, teams that have a mono repo, but they have different branches, you know, they work on their own branches and later all merge together, right? How does it go about handling that? Or is that, again, something, is that an issue for your continuous integration?
I'll answer this by the same question of how does the system already work? Because it arguably does the same thing. So basically, your client runs this.
So you're building artifacts and you store them in a CIS, and so you have maybe two different branches storing similar artifacts in there. How do you disambiguate that?
Is this so this is, we're referring to Bazel. Like, I just want to make sure I'm understanding the context of where the entry point starts. Are we asking from like, how does Bazel do it, or how does
my questions seem naive because I don't know the tool.
Okay.
Yeah.
So yeah, okay, that's good. So I just wanted to make sure I understood where, because there's two layers, and I just want to make sure we were talking about the first layer, not the second, because make sure I'm answering the question. So the answer here is the way Bazel does it. Different build systems do it different, but the way Bazel does it is you have, Aaron actually alluded to this earlier, you have HTTP archive or something like that. Think of it like it's a tarball or maybe a Git checkout, or there's a bunch of different variations that Bazel provides as build rules. They're technically called workspace rules, is the term they use because it's a different kind of build rule. But the idea is it's just a tarball, effectively, or Git checkout, and it just dumps it on disk somewhere. Bazel manages all that. Your build system just deals with all that. Dumps all the files on disk, and then you say, go. There's like another build rule that just says, like, grab all those files and figure out how to do it. Now, your Git checkout in this example might already have your build files, and under those conditions, you can just say, like, build files are here. You know how to deal with them, and then the rest of your builds can link to that. There's a lot of nuance here that I'm trying to not get really deep into, but the idea is that when you need to change, you just change that version number. That's all it is.
You dealt with them by a lot of configuration.
Yeah. So it's effectively like there's a special file called a workspace file. There's also another way to do it, but I'm not going to go into detail here because everybody who knows Bazel knows the old way, not the new way. It's a big change happened a couple months ago, so let's not talk about that yet. But there's a workspace file that has all the they call them external dependencies. In this case, this would be considered an external dependency. In a monorepo case, it is not an external dependency. It's actually like part of your code. So the idea is that's what we were talking about, the difference between the monorepo and the non-monorepo. So that's how it's done when you're non-monorepo and Bazel's trying to work with it. When you are a monorepo, you don't have to worry about it. And that's one of the big advantages that we're trying to propose, is to say monorepos actually are a really good way to do large systems, because the argument here is that small packages and to do, independent, what's it called? Isolated, libraries and packages and stuff. That's really good when you're smaller, and it grows pretty well until you get to this like midpoint. Once you hit there's just like some magical midpoint, and what ends up happening is you have all these dependencies, and you're trying to say, oh, this thing needs version 1.7, and this one needs 1.6, but now I have another one that requires both. How do I do that? And that's where it gets really hard. And so the idea is that your CI system, all of that stuff should just work across everything. The reason people have never done, like, they stayed away from this for so long is because how do you run every test on every single person pushing every single PR in a 1,000-person organization? Well, caching, that's how you do it. Remote execution caching actually solves this problem because it materializes on individual level. And so your overhead is negligible. It's building, I mean, I personally implemented this, building 120,000 artifacts. I've seen that get done in about 7 seconds. I don't know many systems that can do that. So, and that's with a full cache, obviously, but that's the intention here.
So how much compute was that when you did that with that many artifacts?
16 cores.
Oh, okay.
Yeah, you're just hashing. That's all it is. Just now it's Blake 3, so it's even faster at hashing. But just hashing.
The beauty of it is that you never rebuild anything that you have built before. So it kind of doesn't matter how big the build graph is, because if you have built the thing before, you know that it's like, if your inputs haven't changed, then it's a no op, or it's like a lookup op or something. But it's not like, it doesn't actually invoke a compiler.
So there's this one other cool thing that I just want to mention, because I know we're a bunch of nerds here that like interesting tech and interesting algorithms. Bazel has this idea, this concept called build without bytes. It's the only build system I know of besides Buck 2, but Buck 2 is not quite ready for mainstream. So someday we're going to get this talk and it's going to be about Buck 2, just not today, sadly. Buck 2 is written in Rust, by the way, cough, so it's thumbs up there. But they have this concept called build without bytes. What's so cool about build without bytes is that you don't actually need to download your artifacts. It's so cool. Think of this for a minute. You have your source files, super cheap, really small to hash, right? It's maybe a couple thousand files or something like that. You just hash those files, and then you just hash the hashes of the files, and then hash the hashes of the files, and then you just keep hashing the hashes of the hashes, and then you go to the cache and you say, hey, what's that hash that I just, oh, here's another hash, and then you hash the hash of the hash. And I'm serious, that's all it is. You're just hashing hashes now. And then you get to the final thing. You're like, I have the final thing, this one hash. If I look this up in the database, in the cache, if I look this up, it's going to give me the instructions and all the files needed, or download instructions, and I should say, to download all those files, to be able to build it, and all the build instructions needed to compile it. So I have the hash, and then I say, do you have it? And it says, yes, I have the binary you're looking for. And it goes, great. Let me just download the one binary. I just skipped over all the object files. I didn't download anything in between. So that's the super cool part.
One potential application of this is, for instance, when you have LLVM and you want to experiment with like custom, like a custom patch in LLVM, you need this custom Clang binary, but maybe you don't want to download the entire LLVM artifact, like intermediary artifacts. So with build without bytes, it's like you make this change and all the execution happens in like a remote, like a distributed fashion. And the only thing you download to your actual local machine is the final executable. And all of this happens automatically. So even though on the remote execution servers, a bunch of artifacts are created, the thing that you're actually after is like the only thing you download.
What's this configuration, the granularity generally? So if you're doing a big C++ project, is it at the .o file level versus, or is it just sort of dependent on your project, how you kind of manage these intermediary dependencies?
Theoretically, you could go down to the LL, like the bit code. It's totally up to you. So you can define the actions yourself. If you need, for instance, assembly outputs or something, you can do this. by default, what most rules do is, or at least the standard C++ rules, they do work on the C++ level. So you have like one CPP file, means one action. And it's also a fairly common practice to bundle a bunch of CPP files into one rule definition, which will then expand out to several actions.
So similar to how you in Make would have either mapped individually or had catch-all rules that would map all. Okay, so it's the same concept.
Yeah. I would argue that,
but by default, so we'll use C++ because the way Rust rules are done, because Bazel does support Rust, there's a Rust rules definition, which if you want an example, you can actually look at a repo. We implement both for Cargo and Rust. So we're one of the few that fought through that battle. It wasn't fun, I'm not gonna lie, but we did. But the C++ rules is an example, because I think that's where like a lot of people kind of, that the source of truth is usually look at C++, then look at everything else. The way it's suggested to be implemented, the way kind of the default is any file that is a CC or .c or one of those kind of like the link level binaries or objects, I should say, link level objects. That's where it would generate a .o file on behalf of you. So it kind of does it automatically. In Bazel, it's kind of confusing, like not to lie, because what it will do is you would express a rule to say like, my lib, and then you would say, here's even a couple CC files, like you would list all your different CC files. Then you say, here's the header files I want, and then here's the dependencies. So that's how you would normally do it in Bazel. Under the hood, it's going to materialize that into multiple GCC calls or whatever Clang calls. And then it's going to generate a .o file for each one of those .cc files by default. So it actually figures out, it kind of like has some magic under the hood for that. And then the header files get passed around to everybody that depends on it. That's how by default it works. There's a little bit of nuance there when you're dealing with what's it called, header compiling, or C++ has a couple modules and C++ modules, and there's C++ header objects, I think they're called, or something like that. In Bazel does support it, but it's like, to be honest, I've yet to see somebody implement it successfully. It's just too hard.
Modules don't work with the official rules. Actually, the rules that I wrote, that's the one that supports modules. So C++ modules are a bit of a problem in Bazel right now. This is, however, even if you would have a rule set that support this in remote execution, it wouldn't properly work. So, for instance, the current implementation forces module compilations to work locally, because Clang just has internal issues where absolute paths to source files are just leaking into these builds. These are super, super subtle issues. And so the compiler itself just doesn't properly do things right now. So yeah.
Which, by the way, I just want to mention another small reason. It's actually kind of a big reason, but so I worked at some pretty big companies, and one of the reasons NativeLink exists is actually because these companies actually fought a really frustrating problem, which is the fact that on the machine that runs the stuff, it will leak stuff into the build. It's a very frustrating problem. And the solution turned out to be, well, why don't we just run every single GCC command in a pod, in a Docker container, a containerd, whatever, something along those lines. Just make sure it's guaranteed to be isolated. That's harder to do without using remote execution. It turns out that that is the solution. Well, if you're going that far, just take it one step further and parallelize it. So it turns out it just all solved the hermeticity, the making sure that people are doing things correctly. There's not like the previous thing that built, especially on a CI machine, the previous thing that built on the CI machine doesn't break the next guy because they changed a version of something. It fixed a lot of those things.
And you referenced sort of the difference with a Rust build is the level of granularity, typically sort of the crate level, and so binaries and libraries.
Yeah, I made a comment kind of passing that said like it was very painful supporting both Bazel and Cargo. That was one of the big reasons, is because Cargo's way of building everything is just put a whole bunch of your Rust files together into one package and we'll compile it all at one time. Like under the hood, there's magic on how it does it, you know, but the thing is Bazel doesn't, that's not really its preferred way to do things. It really wants you to do like, this file is its own rule. Like it's like it wants the C++ way where you have a header and a CC file, or you know, C+ CPP file, something like that. So it wants you to do that. But in Cargo, if you do that, it like, for example, there's no such thing as a pub crate anymore. Like that just doesn't exist, because there's only one file. And so originally it was done the C++ way, and then it was when we tried to integrate Cargo, there was a bunch of weirdness, and then we lost like a ton of optimizations because the way Rust C goes into IR code and the way it annotates it and stuff, you end up losing a lot of inline ability. And that sucked. And so dealing with like how it decided to inline functions, it required us to go in and put inline in all these places. So the Rust made a couple interesting design choices. I'm not gonna lie, like I'm not in favor of a lot of them, personal opinion. But the thing is like it's a great system. Like the Cargo is amazing for what it does. It's just a different paradigm for how traditional C++ developers are coming into Rust and look at the problem. It's backwards almost.
Something we do to so in NativeLink, we use Bazel for its incremental builds during development. The final executables are built with Cargo wrapped in Nix. So basically we take we use a default standard kind of Rust build for the actual like production builds. But because Cargo doesn't have this nice kind of incremental thing to it, that's why we use Bazel during development, like for instance like run single tests and so on. So we actually, when we added this Bazel Cargo, like both of the builds, originally we had one base, like we tried it with one Bazel target, like what happens if we just do it basically the same way that Cargo does it, and then of course we lost all the incrementality. So rebuilds would just rebuild everything. And then the thing we had in the very beginning was the extreme Bazel way of doing things, where we had every single file differently, and a bunch of like very non-standard kind of Rust the module, I don't remember exactly, like things in place to make it work with Bazel and still be like valid Rust. But if you looked at this, it was very confusing from like a naive Rust kind of perspective. And so what we ended up doing is going the middle way, where we now have a bunch of smaller or medium-sized crates. So we get incrementality for one of those, like for those crates. And that was like felt like the best kind of middle ground between the extreme Cargo and the extreme Bazel build. So like medium-sized like granularity, like
So without knowing any Cargo internals, and also I don't understand the details of what you were talking about. Is there a chance you were testing that during a period when Cargo incremental builds were turned off because there was a bug for maybe 2 months or so? From memory, a year and a half ago?
So the Cargo incremental builds, I'm pretty sure we didn't get caught up in this. I do remember this, but I'm pretty sure we did like a big Rust jump, like an 8 month or something jump, and I think that bug was in that gap, because I think we went directly from whatever the like early version of supporting version 2018 to 2021, I think it was, and we did a big jump, and now we're like keeping up consistently with the newest versions of Rust C. But to answer the question, no, what Aaron was referencing is essentially the Bazel incremental builds was the one that we were having trouble with. Cargo does incremental builds pretty well. Like there's no real big problems with it, but it doesn't have the parallelization that Bazel gives you. So in referencing, like, of course, you would say, well, yeah, I have a 64 core machine and it uses all 64 cores. Yeah, but it doesn't give you 1,000 cores. Bazel does. That's the difference.
And sorry again, without knowing most of it, does it mean that Bazel doesn't use LLVM for that, or does some magic? Because as I understand, the biggest parallelization bottleneck with Rust is LLVM, or maybe whatever, monomorphization and linking optimization part.
So we're talking about different parallelizations here. So Aaron might be able to answer this a little bit better, but I'm going to start from how I understand it. Again, I'm way more familiar, sadly, with the C++ way of doing things. But from my understanding, the way Rust, okay, so understand Cargo is a build system just like Bazel, and then there's Rust C, and Rust C is the equivalent of Clang. I was about to say GCC. I was like, no, but it's equivalent of Clang. Clang and Rust C goes into LLVM's IR code. And then the IR code then gets optimized, and that's where all the optimization layers happen. And then you end up with your object files and binary files from the output of that. There's some nuance there, but very high level, that's the way the majority of it works. However, to my understanding, the Rust C is still compiled on a RS level, like a Rust, an individual level. It will bundle those into an object file, but that part of the compilation, to my understanding, at that phase. But again, it generates, the way to think of it is like, but then it bundles all those up into one object file. And so there's like remember, there's multiple phases in there about the way lifetimes work and the way the public visibilities and stuff work. It like mass them in different layers, and then it does the again, this is where Aaron's going to get better at this, but it does the front end and then does those parallelize, and then it brings them into one optimized the back end, which is where the optimizations happen, which is where the IR. So it generates the IR independently, and then it does the optimization layer, which then generates your object file, and then that's your final output. So correct, but it's actually Rust C, not your build system, if that kind of makes sense. And Aaron, if you could fill in any gaps that I might have missed there.
Sounded all right, like sound correct.
And I want to be, I am not an expert in Rust C. Please don't quote me on any of this. It's just, to my understanding, this is the way Rust C works.
Yeah, like, I mean, I think actually the long build times in Rust are usually, isn't it just linking?
Yeah, which is that final, like, so there's two phases, because so when it generates your object file, it's effectively linking, is the way to think of it. It's actually, there's remember, because it starts with a bunch of individual RS files, and those RS files should be thought of as CC or header files or a combination of both. That's what I'm trying to emphasize. It's like you're effectively taking a bunch of CC files, compiling them as one unit, but keeping them separate from the front end's perspective to generate IR code that's separate. That generates the separate IR code, and then there's the bundling all those together into one object file, just like C++ does, but you don't get the naming collisions. That's the difference.
Mm-hmm, mm-hmm. I would have to look into this more. I'm like, yeah, but like on like regarding the question of parallelization, I'm not sure.
I have a question that's probably less aimed towards NativeLink, but in general, like CI, like CI pipeline and the build caching is in a CI pipeline, there'd often be multiple steps that do the same work. For example, you might have a cargo build as one of the steps in the Docker file, as well as you're also going to run tests as part of your CI pipeline, which will also run cargo build. So is there any solution for this problem where multiple independent steps, right, that ideally would run in like a separate isolated execution environment, try to do the same work and basically using a cache there.
Okay. No, I'm laughing because you're not doing anything wrong, but you're thinking like the traditional separating your build system and your CI system. But if you actually think about it, their job is to do the same thing. Bazel is also a CI test system. It does both. Because if you think about, remember I made the comment saying it's just take your Merkle tree of your file systems, put it up, and then generate a bunch, take your environmental variables and then the command line that you're trying to run and the host that you're running on, like your container or whatever. If you remember, I said it takes that and it hashes it and it gives a well, it's all hash. So you made a comment saying, well, like to keep them from running the same. Well, it's the hash. It just ask, have you seen that hash before? And it says yes, and then you don't need to run it. This is a little, I'm going to go into NativeLink for a second, but like if you pass that through the cache and you miss, then your client is then going to go to the scheduler and say, okay, please do this for me. It's going to hand that to it. Internally, our scheduler actually uses that same key, that same hash, and it will join every single person that asked for that same job to the same thing, and it only executes it one time. You could have 1,000 people that said, can you execute this run for 10 hours job? And anybody that asked for that thing that took 10 hours is going to get the exact same job. The last guy, it's like 1 minute from finishing. They're going to get it in 1 minute. The first guy might take 10 hours. You see, so it's going to like when you attach to it, you happen to attach at a good time. So you win, but it's just a reduction to improve efficiency is what I'm trying to say. However, the question that you had is like, how do you do that? So that's what we're kind of saying. Like, if you put your tests into a system that implements this protocol, it fixes this problem. Like, don't separate your building and your testing. It's all just a dependency tree. So once you're done building, take it and hand it to your test, and then consider that a build job. It's actually a test, but it's the same thing. To it, it's just go execute this thing and give me the results. And then it just dumps them. And the only thing that Bazel, the only reason it treats them different is just it materializes them in your standard error, standard out different for if it's a test or a build. Because if it's a build, it considers like, stop the world, your build completely failed. What's the point of continuing? But if it's a test, it goes, your test failed, but I'm going to keep running everything else. That's the only difference of how it treats it. But that's a client thing, not a back. I don't know if that answered the question, but that's one point. I did want to bring up one other really cool concept that is, if you take this to an extreme level, which I don't think I've actually ever seen any company take it to this extreme level, but I need to compile for ARM, x86, PowerPC, and all these things. Well, in theory, those are just go build all of them at the same time. It's one client, one machine. It has all the tool chains in place, it has all the source files, it's all the same, and it's just going to do all of them. So you have one machine, it just says, go do everything at one time, hands them off to some scheduler in this case, and then scheduler hands them off to the nodes that are capable of compiling them, collects them all together, runs the tests, gets all the results back, and it just displays the test. It doesn't actually do anything local. So that's the kind of the reason we're like, hey, actually, this is what community should be using. This is the right way to think of it. That's kind of our push. So don't think of them as separate things. Did I answer the question? I should make sure if I didn't sidetrack it.
Yes, no, it does. I'm not super familiar with Bazel, so I think my question was towards, if you're not using this like a single tool to handle all of that stuff, is there like some theoretical way or that someone has like tried out to, without having this tool that like manages everything, right? That's aware of it, but more of that just some way of caching the same basically like execution steps that multiple independent tools do, such as, for example, when you build a Docker, like a Docker image, as well as do the same cargo build as part of the like a GitHub action that you define.
Have you ever used GitHub Action Cache?
Yeah. So I was gonna say something that might be interesting to look into is the magic Nix cache action for GitHub Actions. That's when you use when you run cargo. So you could look at we use this in NativeLink as well, in the NativeLink CI. So we do have GitHub Actions as well for like the regular repository. And what that does is we wrap the cargo build in a specialized, I guess, kind of specialized Nix builder that builds a cargo project. And that builder takes the different, like the dependencies, like the crate dependencies, builds those separately in it's like the unit of execution, like each crate is one compile thing. And then it caches all of those crates as separate derivations in your GitHub Action cache. So instead of having one single big cache that's like maybe 4 gigabytes or something for the project, we have like 10,000, and we had a bug yesterday, so then it was like 60,000 different caches, like different caches in GitHub Actions. This way you can kind of share artifacts, like common artifacts, you can share those between different jobs. So that can be a very nice thing, and you get higher cache efficiency out of this approach than when you use a regular, like I dump everything into one GitHub Action cache, because maybe you have, let's say you use Ubuntu 22 and Ubuntu 24 by default, like an unair-gapped cargo build. These artifacts would be entirely different, because like linking, for instance, would still use different linkers from the host. If you wrap those in Nix shells with like just a Nix build, you have the same linker on both of those systems, and so then you can share the cache between these two jobs, and this brings down your your cache usage substantially.
Oh, I see. Interesting.
So I will say there is the very naive approach, which is probably where most people start. And Aaron's going to shoot me for saying this because he's our hermeticity king. Most people, the way they do this is they actually just use Docker. So they use a Docker file. They just start from the top. They just say install these things, and then they say the next line, build the things that don't change much. It's important. So they know these things aren't changed very much. So maybe external dependencies and stuff like that. And then the net line under that would say, okay, now build my code that doesn't change much, and then build the things that actually change a lot, and then link it all together. The idea is that then you're utilizing Docker cache to actually jump to that spot, but it's not very fine-grained. And we actually did this, the very early versions of the CI for NativeLink CI. We originally did this. We hit the 10 gigabyte limit, like one build, like we're done. We couldn't, like, it made it, we eventually removed all that code and like went to a whole different thing, because we couldn't even pay GitHub to give us more space, so they wouldn't even take more money from us. So whatever. I don't know what Microsoft is thinking. Please take our money. No. You're asking for more than 10 gigs. That's another hard drive. I don't know.
They the Docker, what was I got this? One problem we also had with the Docker approach is perfect like SBOMs. So this like software bill of material. It's way harder to get a Docker build truly reproducible. Like if you want to actually pin all your dependencies, writing a Docker file that pins everything is so tedious. And also Ubuntu just updates their repositories, and they tend to just delete certain packages. So even if you do this, next week your build might just might not work. And of course, you can get around this if you host your own mirror of the APT repositories, but then that seems to be an awful lot of overhead for smaller projects.
And now you're dealing with secrets, and you're dealing with a whole.
Yeah. So it's like, yeah, and instead, it seems a lot easier to just just take something that is designed to be reproducible by default. Yeah.
One of the other small things, I'll just do a small note here, is by actually separating your CI jobs and your workers and making sure that they're separated from your users, you get this really nice side effect, which is I worked at a company at one point where you were not allowed to see certain code. So it was like, because there was like the super sensitive code, and now we actually there's a way for them to actually like build stuff into and link against it, but not ever be able to see the code, because they would only get the hashes effectively. So think of it kind of like a pre-compile, like, think of it like a SO file that you're linking against or something, but it's not. It's actually like you get full text files with lots of like, details in it. You can do anything you want at that point. So this is really useful, especially for certain logins where you're potentially mutating public-ish state or reading public-ish state, where it might be sensitive for users to be able to do that themselves. So.
All right. Unless there's any other questions or comments, I think we can probably wrap things up here. So, yeah, thank you all for attending today. I'm very glad to have such a great turnout today, especially in person as well. It's more than I had expected. So, yes, thank you all for coming. And yeah, I don't really have much else planned today. Oh, Marcus, do you have a question? I saw you raise your hand there. Maybe that was just a clapping emoji. All right, but yeah, yeah. Again, thank you all for coming. Next month probably will be another talk. I'm in talks with someone else who wants to prepare another presentation. So yeah, look forward to that. If it's not them, then I might try and throw something together for next month, or we might just have a free talk.
Yeah, and just one thing, if you guys want to learn more, I put the Slack channel on the G message thing, the Google Meet message. So we'll be hanging around there too.
Well, thank you. Yeah, and by the way, if you want to upload the slides at all anywhere, we do have a repo, a talks repo. If you want, you can upload your slides there, and
yeah, sounds good.
we'll also post the recording for this meetup on YouTube in the usual place. Just send out the link to everyone after the meetup, and once it's been uploaded, and you can check it out there. All right.
Yeah, thanks for hosting.
Thanks for hosting.
Thank you.
Yep. So,
Bye.
yeah.
Thank you. Bye.